Hello everyone. In today's session we'll learn about water turbines. We'll see how a water turbine works, what are its classification and what are the usage of it. So in this particular session we'll be learning about classification of a turbine, construction and working of a Pelton wheel, Francis turbine and a Kaplan turbine, and we'll also compare these three turbines based on the applications of it. Now let us understand what is a water turbine. A water turbine is a prime mover which converts a potential energy and kinetic energy of water into a mechanical energy. Here, the kinetic energy of water from the penstock enters the turbine and a mechanical work is getting converted. So this is about a water turbine. Here, based on the application, we are going to use three types of water turbines or many types of water turbines. Basically, we'll be learning about a Pelton wheel, Francis and Kaplan turbine. As you can see in the diagram here, over here, you have got a reservoir, a penstock here, the turbine here. These are the three major components where the water flows from the reservoir to the turbine, converting this potential energy into kinetic energy and finally into mechanical work, that is rotation of this shaft. And the power is transferred or developed using a generator where we use a step-up transformer to supply the power through transmission lines. So this is about a hydraulic power plant. Basically we'll be learning about the turbine here. So if we need to look into the classification here, so we have basically three types of classifications. One is type of energy available at the inlet. So we have got two types of energy that is available at the inlet. One is impulse and one is reaction. So it depends on the force what is applied onto the turbine blades. This impulse and reaction force you have already learnt in steam turbine. I won't be explaining this impulse and reaction forces. So basically a Pelton wheel works on a principle of impulse force, that is why it is called as impulse turbine or a Pelton wheel here. So Francis and Kaplan turbine are classified under reaction turbine, where the reaction force is applied on the turbine blades. The next classification is head at the inlet of the turbine. This means the pressure head that is available at the turbine end. So you have got a penstock. The more the pressure head, the more will be the power developed. So we have got a high head turbine, medium head turbine and low head turbine. So again we are going to classify each turbine under high head, medium head and low head turbine, okay, based on the direction of flow of water. So it depends on the flow of water inside the turbine. So a small modification is done for the flow of the water here. So tangential flow turbine, axial flow turbine and radial flow turbine. So here I have classified Thomson turbine under radial flow turbine, which we will not be studying in this particular syllabus. So as you can see here, the first turbine is a Pelton wheel turbine, which is very simple to understand. You can see the diagram over here. You can see the diagram over here. So here you have got a penstock and a spear here, which acts as a nozzle. The water impinges onto this Pelton cups, and the Pelton cups is affixed to the runner here. So Pelton cups is also called as buckets. So this buckets which is fixed to the runner, when the water impinges onto this blades or cups, it starts rotating about the axis. When it starts rotating about the axis, the other end of the shaft is connected to the generator where the power is developed. So in order to stop or in order to have the uniform torque on this particular runner blades, we use something called as brake nozzle. So this brake nozzle stops this buckets that is rotating in the circumferential direction or a centrifugal force. It stops and we'll get the uniform torque here. That is the importance of this nozzle brake or brake nozzle. So here we have got the casing here. So the entire water that is hitting this blades enters the tail race and goes through the channel. This is how the power is developed using a Pelton wheel. But we need to understand how the electricity is generated here. As you can see the animation here, through the penstock the water passes and hits the Pelton cups, right? So as you can see the load is applied here or a bulb is lit here. So this is how a Pelton cup works. If I need to increase the efficiency of the Pelton wheel or a Pelton cup, so we are going to divide this or bifurcate this flow of fuel here. So we have got Pelton cups here, which is specially designed in order to increase the centrifugal force. You can see in this particular diagram you have got two Pelton cups here. Parallelly there are two Pelton cups that is placed. So when the water impinges onto this Pelton cups, it splits into two directions, where increasing the centrifugal force. So this is how a Pelton cup actually works here. So we use a gear mechanism here in order to provide or in order to use with the uniform torque. So the generator is connected at the end of the Pelton wheel shaft and uniform torque is generated. That means uniform power is developed throughout the process. So this is about a Pelton wheel, but what is the takeaway? What you need to understand here is you need to draw this particular diagram. This is a diagram that you need to draw. You need to understand a few concepts here. This Pelton wheel is a tangential flow impulse turbine. Water flows tangentially along the Pelton cups here, and it is impulsive force that is acting on the blades. That is why it is classified under impulse turbine. It is used for high heads. So more the pressure head, more will be the power developed. So this particular Pelton wheel turbine produces more power because you have got high head in the pressure or in the reservoir. So high velocity jet of water from the nozzle is made to impinge on the curved blades known as Pelton cups that is fixed around the runner. So this particular Pelton wheel can produce a power up to 200 megawatts with a pressure head of 1000 meters. So the penstock or the height, the difference of height between the reservoir and the turbine will be about 1000 meters, and the rotation of the Pelton wheel is about 3 meter per second. So which is rotating at higher speeds. Now we'll look into the Francis turbine. See, there is a lot of difference between a Francis turbine and a Pelton or a Kaplan turbine here. See, this Francis turbine is a reaction turbine, medium head turbine. As you can see in the animation over here, this guiding vanes can be adjusted. So this is a scroll casing. We'll see in detail in the next slide. So this is a scroll casing where the water or the pipe gets converged here. The water enters at high speeds and passes on to this guide vanes. So this is the water passes radially here. That is why this turbine is called as a radial flow turbine. As you can see, the water passing here, the water passes through the scroll casing and enters this runner blades and passes through the tail race or the draft tube. Okay, so here these are the guide vanes which guides the water here. These are the runner blades where the water hits this blade, and because of the centrifugal force the power is developed in the shaft. So this shaft is again connected to the generator where it generates the power. So this is about a Francis turbine, which is easy to understand. But what is which diagram you need to draw in your notes is this one. You can see here. So this diagram you need to draw in your notebook, right? So you have got both stationary vanes and runner blades here. So from the penstock, the water enters through the scroll casing and enters through the stationary vanes or guide vanes. We call it as guide vanes. So this guide vanes guides the water at a particular inclination where it hits the runner blades, where the maximum centrifugal force is produced on this runner blades. So because of the maximum centrifugal force or the resultant centrifugal force, this rotates at greater speeds, and the power is developed at the end of the crankshaft or at the end of the shaft here. So this is the top view and this is the front view of the turbine, right? The same diagram is given over here. So here you can understand, here in this particular case, in this particular diagram, you can see the draft tube that is enlarged at the lower end. In order to produce the section or in order to have the suction force at the end of the draft tube where the water has to go out of the turbine. So to increase the pressure, the draft tube, the cross section of the draft tube is increased. So this is about a Francis turbine. So next we'll move on to the Kaplan turbine. As you can see here, as you can see in this diagram, the water flows through the scroll casing and enters axially through the guide vanes or the stationary blades. So that is why it is called as axial flow turbine. Since the water enters axially inside the turbine, this is called as axial flow turbine, and it hits the blades over here. This is similar to your propeller shaft. That is why this turbine is also called as propeller shaft turbine, right? So it hits this blade, the water hits the blade. These blades are aerodynamically designed in such a way that the maximum centrifugal force is given to this particular shaft, right? So the water flows onto these vanes providing maximum centrifugal force and produces the power here. So these are the two diagrams that you need to draw. You can draw either this diagram or this. So it is better to draw this diagram where it clearly shows that the water entering from the penstock through the scroll casing, and it passes through the guide vanes axially and hits this runner blades or runner vanes, and it goes out of the draft tube and to the tail race. So this is how a Kaplan turbine works. So you can compare now the Francis and Kaplan turbine. Here you can see it is a reaction low head turbine, but Francis turbine is a medium head turbine, and this particular turbine is axial flow turbine, but the Francis turbine is radial flow turbine. So here also, when water hits this guide vanes or the runner blades, the velocity, the pressure head is converted into a velocity head here, right? So efficiency of this turbine is over 90%. So in most of the applications we are going to use Kaplan turbine for power production. So in most of the hydraulic power plants we use Kaplan turbine, but instead for a medium head turbine we go for a Francis turbine. So this is about a Kaplan turbine. Now I've just added a video of comparing a Pelton wheel, Francis and a Kaplan turbine. So you can watch this video. I've taken it from YouTube, so you can watch this and you can compare these three turbines based on their applications. So this was about the turbines, which is very easy. So I want everyone to draw these diagrams in your notebook and submit this as an assignment.
Pelton, Francis, and Kaplan are the most commonly used hydraulic turbines. In this video, we will compare these three turbines and see when to use which turbine. When we move from Pelton to Kaplan, the force-producing mechanism changes from impulse to reaction. In Pelton, pure impulse force of water jet is responsible for rotation of impeller. Water stored at high altitude can produce high impulse force due to its high velocity. So Pelton turbine are suitable for operation when water energy is available at high head and low flow rate. Whereas Kaplan turbine is suitable for the reverse case. A high water flow will guarantee efficient production of reaction force. So when water is available at high flow rate and low head, Kaplan turbine is the best choice. Francis turbine comes in between for medium head to medium flow rate applications. Francis turbine is not a pure reaction turbine. A portion of force comes from impulse action also. This graph gives a clear idea about when to use which turbine, depending upon available water head and flow rate. It is obvious that Francis turbine covers a wide range of operating conditions, or they can work efficiently in wide range of operating conditions. This is why Francis turbine is the most preferred hydraulic turbine. If you use a turbine out of its recommended operating range, it will work, but less efficiently. It is also interesting to note the direction of fluid flow with respect to axis of rotation in each case.
So much for watching this video. In the next session, we'll be learning about the concepts of boilers, classification of boilers, working and construction of Lancashire and Babcock and Wilcox boiler. So these two boilers are classified under fire tube and water tube boilers. So these are the concepts that we are going to discuss in the next session.